So those of you who know me will know that I love testing. And in particular, I love property-based testing. But I found out fairly recently that many people actually find it quite tricky to come up with good properties to test their code with. So I thought today I would try and demystify that a little bit. Now, I am going to talk about testing pure functions. So if you're sitting there thinking, when is he going to start talking about testing code with side effects? The answer is not today. But don't worry, it's going to take me a full hour to talk about testing pure functions. So baby steps, you know? And I'm going to be giving today's talk using Haskell for the examples and using Haskell Quick Check as the property-based testing tool. But the ideas are going to be generalizable. So whatever property-based testing tool you like to use, you're going to be able to take these ideas. And I hope you'll find them helpful to write properties of your own. So let's start off. For those of you who maybe haven't come across property-based testing, I'll just explain what it is. Let's take a really simple example. The reverse function on lists. So suppose we wanted to test that. Well, of course, it would be easy to write a unit test, right? Here's one. And this is just an example of the form that unit tests so often take. We call the function that we want to test. We make up some sample argument for it. We figure out what the result should be. And then we check that that is actually the result that's returned. And this triple equal sign, that's just an equality test. But it's part of Haskell Quick Check. It'll generate an error message. And the test will fail if those two values are not equal. OK, so that's straightforward. Do I like it? No. I'm only testing reverse on one input. What about all the other lists? So what I like to do instead is to write a test for reverse using Quick Check. What does that look like? Well, I just define a function for testing reverse, a function I call a property. And so I'm calling it prop reverse. It's going to take an argument list, x's, and test reverse on that list. And the great thing about this is that Quick Check is going to be able to generate arguments for this function. So I'm going to be able to test reverse on thousands of different inputs, millions if I want. Excellent. You'll notice that even though reverse can reverse lists of any type, I've written a type signature here, list of integers. And the reason I've done that is I need to tell Quick Check what kind of test data to generate. So you'll see some type signatures. They're there just to choose test data. And I'm going to use lists of integers because why not? Integers make quite good test data. OK, so now I'm going to be testing reverse on a random argument. That's great. But of course, I haven't finished the property yet. I need to write something in place of the question marks. What shall I write? Well, in the case of the unit test, I knew what the argument was. I could figure out what the result of reverse could be, and I could just compare against that. But in this case, the expected result of reverse is going to depend on x's, isn't it? Well, of course, that's no problem. I can just write a function to compute it from the argument. Yeah? But that isn't actually any easier than writing the reverse function, is it? Because it is the reverse function. Now I'm going to write the reverse function twice, once in my code and once in my test. And do you know what's really stupid about that? If I've made a mistake in the reverse function the first time I wrote it, I'll almost certainly make the same mistake the second time I write it. So that means not only am I doing the same job twice, but there's little value. I'm going to be making the same mistakes both times. I've gone to all this trouble of writing a property. And it's like back in high school when you did lots of algebra and you proved that 0 equals 0. Right? It's not actually going to be a good test. And this is something that people encounter all too often when they try and write property-based tests. They replicate part of the code in the tests. That's expensive, because you do the same work twice, and it's low value, because you probably won't find your bugs. Expensive and low value is a bad combination in a testing technique. And some people, when they discover this, they just say, property-based testing isn't for me. The wrong conclusion, of course, but it's understandable. So, what can we do instead? Well, if I can't predict the result of reverse in my test, I have to do something else. What I can do is I can test some property of the result. So, for example, in this test, I test that if you take the result of reverse and reverse it again, you should end up with the list you started off with. Right? That should be true. And now this property is, it's quite easy to write, and I'm going to be able to run as many tests as I like. By default, 100. Okay, so that in an instant will test reverse in 100 random cases, and I can go on to test many, many more. There's just one problem with this. What if I had written reverse in this particularly stupid way? Now, you might think, surely nobody is that stupid. But sometimes I don't want to write the code of a function straight away. Maybe sometimes I just want to put something there to keep the type checker happy and go on, and I'll come back to that later. Well, what if I forgot to do that? This will keep the Haskell type checker happy, but that definition will pass my test. Because it's also true. So that's sad, but what's particularly irritating is that if I make this mistake and I run that unit test I showed you in the first place, of course it will detect the bug. So what have I done? I've gone to all this trouble to write a property-based test, and perhaps I've got worse testing than when I started. That's not good. Well, now, of course, I can write a property that will distinguish this wrong definition of reverse from the correct one. Here's one example. This is a wrong property. It tests to see, have I written the bad definition? So it just checks that reverse x's really is the same as x's. And if I test this one with quick check, because my reverse is actually correct, I can write reverse. Of course, this property will fail. So this gives me a chance to show you what happens when a property fails. Quick check will complain, and it will produce a counterexample, a failing test case. In this case, the list 0, 1. And why does it fail? Because when you reverse it, you get 1, 0, and that is not equal to the original list x's. So it fails the wrong property there. The interesting thing here is that quick check almost always will choose 0, 1 as the counterexample. Occasionally 1, 0, never anything else. Now, I told you that quick check is generating random test cases. What's the chance of hitting 0, 1 as a random list? It's very, very small. The reason that we see this particularly simple test case is that quick check, after generating the random test and finding one that fails, has simplified it as far as it possibly can. We call that process shrinking, and in this case, shrinking will discard unnecessary list elements. We only need 2 to falsify this property. And it replaces integers by smaller ones if it can. And so that's why we get 1, 0. Why don't we get 0, 0 as the list? Because when you reverse 0, 0, you do get the same list back again. So that's not a counterexample. So the smallest counterexample is a list with 2 elements, 1 and 0, and they might appear either way around. Okay, so that's a quick introduction to property-based testing. And we've seen 2 of the great things about it. First of all, that we can randomly generate lots and lots of test cases, as many as we like, and so get much better testing, hopefully. Secondly, it's really important that when a test fails, we don't see random blah. We see a really tiny example that is usually very easy to debug. But we've also seen the trap, that it's often very tempting to replicate your code in your tests. And if you do that, you're really wasting your time. It's expensive and low value. So what I'm going to talk about today is I'm going to try and show you 5, if there's time, systematic ways of thinking about how you can formulate properties for property-based testing. To do that, I'm going to need a simple example, but not as simple as the reverse function. And so I'm going to use binary search trees containing keys and values. So this is just a representation for finite maps. And I'm sure everybody has studied binary search trees at some time in the distant past, maybe. But we're going to test a Haskell implementation of them. On this slide, we see the definition of the Haskell data type, that a binary search tree with keys of type K and values of type V is either a leaf, representing an empty map, or a branch. And a branch node contains a left subtree, a key, a value, and a right subtree. So that's the data structure that I'm going to test. Of course, I need to test operations on the data structure. So let me show you the operations I'm going to work with. First of all, one that can find a key. You give it a key and a tree, and if the key is there, maybe it'll return you a value. I've got 4 ways of building trees. Nil is going to build an empty tree. Insert can insert a key and value into a tree. Delete deletes a key from a tree. And just to make things a bit more interesting, I'm also going to use union, that given 2 trees gives you a tree that contains the contents of both. So these are the 5 functions that I'm going to concentrate on testing. You will also see a couple of other functions here and there in the talk, but they're not interesting to test. They just help me formulate properties. ToList is going to take a binary search tree and just return a list of pairs of the keys and values in the tree. And keys is even simpler. You give it a tree, you get a list of the keys in the tree. So you'll see those cropping up. OK, so now I want to write some properties of these operations. But before I can do that, I have to tell QuickCheck how to generate random trees. Now, I could give an entire talk on writing generators, but I'm not going to do that. I'm just going to briefly show you the generator that I'm using. It looks like this. So the code is a bit complex, but what it says is, choose a random list of key value pairs, and then insert them into the empty tree. Okay, so we're going to be able to get random trees by randomly inserting keys and values. I hope that sounds reasonable. I also need to tell QuickCheck how to shrink this type of data. But that's easier. There is a generic method that QuickCheck provides, and I'm just going to use it. So that's fine. OK, so what properties might I write of these operations? So I think the first thing that one should always ask oneself in this kind of situation is there an invariant? And if there's one thing you should remember about binary search trees, it's that, yes, there is an invariant that the trees have to satisfy. And I can easily write a function to check that that invariant holds. I've called it valid. So what does it say? It says, well, a leaf is a valid binary search tree. And when is a branch valid? It's valid if the left subtree is valid and the right subtree is valid. And all the keys in the left subtree are less than the one at the root, and all the keys in the right subtree are greater than the one at the root. Ring a bell? What if you have the value twice? Well, this says that's not valid. Okay, so this is why it's helpful to write this function down. I'm defining what's valid here. And I'm saying you must not have the same key twice. So some of you may be looking at this and thinking, yes, that's obviously correct, but it's not very efficient, is it? No. I could be clever, couldn't I? Because since I know, for example, that the left subtree is valid, then I only need look at the rightmost key in the left subtree and compare that with the one at the root, right? Is that obviously correct? Well, it's plausible. I'm not going to write the code that way. It would be more efficient. This is quadratic in the depth of the tree. But who cares? Generated trees, generated tests are small. You can afford to run a quadratic function. What you can't afford to do is make a mistake in this code. So I optimize my test code for obvious correctness, so that when a test fails, it's not because I screwed the test up. It's because there's really something wrong in my implementation. I think that's one useful lesson about writing property-based tests. Optimize for correctness, not performance. So once I've defined this function, then I can write a bunch of properties. For every way of constructing a tree, I can write a property that says that should give a valid result. Okay, so first of all, the empty tree should be valid. Secondly, if I insert a key and value into a tree, I should get a valid result. Thirdly, if I delete, the result should be valid. And fourthly, if I take the union of two trees, the result should be valid. You'll notice some grayed out type information on this slide. Remember I said I have to specify it? In fact, I have to specify a bit more. I'm also going to say that the keys I'm going to use in my tests will be integers, the values will be integers, and so on. It has to be there. It's boring. I'm going to elide it on all the rest of my slides. But when you try this at home, you do actually need to have it. OK, so now I've got 4 properties testing the 4 ways of building a tree. If I plant a bug, these properties should tell me where it is, right? So let's see what happens. I planted a bug in insert that constructs a tree that is not valid. So prop insert should fail, the others should pass, right? Here's what happens. What? They all failed. So insert valid, the first one fails, I expected that. But delete and union can also return invalid results, even though I did not put a bug in them. What's going on? Well, if we look at the test cases that QuickCheck reports, these are the trees that I passed in to delete and union. Look at them closely. They're the keys in the first tree. Wait a minute. There's a 0 key in the right subtree and a 1 at the root. That's not valid. Likewise, the one that I passed to union has the 0 key twice. I said you can't do that. So QuickCheck is complaining that if you give delete and union invalid inputs, they'll produce invalid outputs. But, duh, I didn't expect them, if I give them garbage, to fix it up so that it becomes a valid tree. What I expected was that if I give them valid trees, they'll produce valid results. So what's going on? Why did this happen? Do you remember how I generated random trees? I used insert, right? Insert is buggy. So now QuickCheck is generating invalid trees and passing them to delete and union. So of course the properties fail. So what this shows us is that when you do this kind of thing, there's another property that you must always write. This one. This looks weird, right? It looks as though it's testing that every tree is valid. What is it really testing? It's testing the generator. It's testing that every tree we generate is valid. And if this property fails, there is no point looking at the results of any others. So it's a critical property. We have to test our test infrastructure so that we can have confidence in the results that it produces. Actually, it's important not only to test that I generate trees, valid trees, but also that when I shrink trees, they shrink to valid trees. So the shrink function that you have to define, it returns a list of smaller trees than its argument. And the property I want to write says that all of those should also be valid. But you know what? Even if I fix the bug in insert so that that first property passes, the second one still fails. Look, QuickCheck tells me that the first line there shrinks to the second line. Okay, and if you look at the second line, it contains the key 0 twice. Okay, that's not good. So in what case does my shrink function do that? Well, I can see the argument I gave it, but what? That is also invalid. So quick check is showing me that an invalid tree can shrink to an invalid tree. Well, again, yeah. So what? Why is it showing me that? So I'm not generating invalid trees anymore, but this still happens. Why? Because before quick check shows me this result, it shrinks the test case using a buggy shrinker. That's why I get a useless result. So you can stop this from happening, and the way to do it is to add what we call a precondition to this property, which says, it changes it to say, if the tree is valid, then everything it shrinks to must be valid. And the effect of that is to tell quick check, don't even run tests where t is not valid. And in particular, don't shrink to tests where t is not valid, even if the shrinking function suggests you might. And if we do that, then quick check reports something sensible. It shows that that first line there, containing keys 0 and 1, which is valid, can shrink to the second line, containing keys 0 and 0. Why is that? Well, quick check shrunk the 1 key to a 0 key. Why? Because I was lazy. Because I said, just use the built-in shrinking function. The built-in shrinking function knows nothing about binary search trees. It just tries to shrink everything. So, of course, it will shrink that 1 to a 0. I need to fix this to get any useful results. How can I fix it? Actually, it's dead easy to do so. I can just say, use the generic function, but only keep the valid shrinking trees. That's the easiest way to fix it. OK, so that's good. We've talked a lot about validity testing, testing an invariant. And I want to emphasize this is important because while just producing valid trees isn't everything you want to test, if your functions are producing invalid data, then you want to fix that kind of bug first. So this is a good starting point. What can we do next? Well, it's always useful to ask yourself, what is the postcondition of each function? Now, I realize this is the vaguest advice in this talk, because it's like saying, what is the property of your function? But nevertheless, it is useful to ask yourself, after I've called, for example, insert, what should be true? And here's my suggestion. After calling insert, we should be able to find the key that we just inserted, and we should also be able to find any other keys that were there beforehand. And I can write this down as a Haskell property. I'll call it the insert postcondition, and it just says that after I have inserted a key and value into a tree, if I try and find any key at all, if it's the one I just inserted, then I should find the value I just inserted. Otherwise, I should find whatever was there before. So that more or less directly translates the sentence into code. This is a good property, certainly worth testing. You might wonder, if you look at k and k prime, those are two randomly chosen integer keys. How often will they be the same? And the answer is, not very. So when we test this property, we're going to spend most of our test effort in the else branch. In other words, testing that insert did not corrupt other keys in the tree. That's important to test, but whether we should spend 90% of our time testing that is another question. OK, so there's one slight problem with this property, but I'm not going to focus on that. It is a good property. I'm going to show you a more serious property with postconditions. And we'll consider another function to see that. What's the postcondition of find? OK, well, let's think about it. After calling find, there's two cases, right? If the key was present in the tree, then we should get just and the value. If the key's not present, the result is nothing. How am I going to write this property? Well, I'm going to need some auxiliary function that can tell me whether the key is present in the tree or not, and if so, what the value associated with it is. But that's the find function. I just took my foot and I put it in the trap. How can I avoid it? Well, there is a nice trick that we can play at this point. We can say, rather than trying to write a test that determines whether or not a key is in the tree, let's write tests that guarantee that the key is in the tree or that the key is not in the tree. And how can I do that? Well, I can write one test that tests find on a tree where I guarantee the key is present because I've just inserted it, and another property that tests find where I guarantee that the key is absent because I've just deleted it. Okay, so those two properties together capture the same intent as the sentence that I wrote previously. So we ensure what we want by construction. There is still a reason to be suspicious of that first property, for example. And that is, it's supposed to test find in every case where the key is present in the tree. But how do I know that every tree containing k can be constructed by calling insert with k? Maybe insert only puts keys in particular places in the tree. So maybe I'll miss some important tests by writing the postcondition this way. Well, if so, yeah, that's a problem, but we're not going to solve it here. Let me go on to another idea, a very, very useful idea for testing, that I call metamorphic properties. And the idea here is that you ask yourself, you say, well, maybe the actual result of a function like insert is very hard to predict. But if I change the input of insert a little bit, maybe it's easier to predict how the two results should be related. Right, so you see what we're going to do? We're going to take a tree. We want to test inserting a key and value into it, but it's hard to predict what result we should get. So instead, we're going to modify the tree in some way, like maybe insert a different key, and then do the first insertion. Now, what can we say about the two question mark trees at the bottom? Well, what we can say is we don't know what either tree will be, but the one on the right should contain k prime and v prime as well as what the one on the left does. In other words, I should be able to construct the one on the right just by repeating the insertion of k prime and v prime. So this is an example of a commuting diagram, and I'm going to write a property that just tests that both paths around the square produce the same result. So I want to think about how many property ideas I can get with this approach. If I've got n operations to test, and if every operation can be used to modify an input, then I get a quadratic number of test ideas. So that's great. This is a really fertile source of ideas for writing properties. When I write the property down, it's always going to relate two calls of insert. So I've called it insert, insert, because we're testing insert with an insertion into its argument. So here is the first call, the original call I wanted to test. Here is a modified call, where I've given it a slightly modified argument. And then there should be some relationship between the two. And that relationship, it could be, I could write a property that tests something as simple as the upper tree is bigger than the lower one. That would still be useful. But here, I'm going to say that actually I can get the upper tree by repeating the insertion of the other key and value into the other call. Okay, so here we are. Here's my first metamorphic property. Now, I can see some of you are looking a little worried. You may be wondering, is this really true? And when I write this kind of thing down, I see many people started thinking, is this really true or not? So here's some more important advice about property-based testing. Do not think. Let QuickCheck do your thinking for you. Is it true? We'll just find out by testing it. And then one of two things will happen. Either the test will pass, in that case it's almost certainly true, or QuickCheck will tell us precisely what case we missed. And in this case, it's not true. The test fails. And if we look at the test case that Quick Check reports, we can see that we're inserting the same key twice. The key 0 is used twice. The property says you can swap any two insertions over. But of course you can't swap insertions of the same key, right? If you insert the same key twice, the last insertion wins. So what, do I have to throw the property away? No, of course not. I can just refine it a little bit. Okay, so here's the property that I actually want to write, where I'll make that modified insertion, and then I can just say, if the two keys were equal, well, I can also predict what I should get. The last insertion wins, right? So it should be the same as just only doing the last insertion. Otherwise, the original thing I wrote. And now I've got a refined property that should be correct. Only it's not. Oh, darn. What happened here? Well, now I've got Quick Check has shown me a test case where I insert different keys, but in different orders, and the order makes a difference. You can see there at the bottom are two trees that are clearly different. But if you look at the keys and values in them, the two trees contain the same keys and values. They just have different shapes. Do I care about the shape of the tree? I'm going to say no. So I'm going to say that morally, this property is true. Of course, now I have to teach morals to Quick Check. And we very often need to do this when we do this kind of testing. So I'm going to define when two trees are morally the same, or equivalent. And I'm going to say they're the same if, when we convert the trees to the list of keys and values, they contain the same content. And then I just rewrite the property to say that the trees that I get by these two routes are always equivalent. This property passes, and it's a really good property for testing. And now I could go on, and I could write, insert with argument modified by delete, delete with argument modified by insert, delete with argument modified by delete, union with arguments modified by, lots and lots and lots of properties. So I get great testing. And this idea of running the code under test twice on related arguments and checking that you get related results, that's not limited to property-based testing. That's called metamorphic testing in general, and it's an extremely useful technique. It's also a research area in its own right. There is an international workshop that runs every year on metamorphic testing with examples of applying it in all kinds of different contexts to all kinds of different software. And that runs together with the International Conference on Software Engineering. So it's a really, really useful idea. Okay. I think I have a little time to show you the fourth idea. The fourth idea is what I call inductive properties, and this is something that Koen Klassen came up with. Koen was my co-inventor of Quick Check in the first place 20 years ago. So look at these two properties for union. The first one says, if you take the union of an empty tree and any tree T, you should get the same tree back again. Seems reasonable. The second one says, if you take the union of a tree built with insert, that's the same as taking the union of the tree you started off with and then inserting the key and value into the result. Also seems reasonable. And I'm using the equivalence comparison there because they might have different shapes. But if you look at these two, it almost looks like a definition of union, doesn't it? Because look at that second one. I'm saying that the union of a tree built with insert can be constructed by recursively taking the union of a smaller tree and then doing the insertion at the end. Now, this is not a suitable definition of union. It doesn't work as a definition. But we can argue by induction on the size of the tree that if union passes these two properties, it must be correct. Only one function should do that, and it should be the right one. Okay, so that's nice. And inductive properties are properties that you write down, and you can make an argument by induction that the only function that can pass these tests is the correct one. In other words, you have a complete test of your code. So that's really nice. But there's a hidden assumption here. And the assumption is that every tree can be built just using insert. Every shape of tree can be built only using insert. Is that true? Well, you could think about it, but what did I say? Don't think. Can I test it? Turns out I can. To do so, I need to write a function that, given a tree, returns a list of insertions that will reconstruct it. And that's easy to do in this case, because it would be harder if I were using some kind of balanced trees, but I'm not. So how do I reconstruct a tree? Well, first of all, I better insert the key and value at the root. And then, because insert never moves keys and values, they'll stay there. So I can then take insertions that will construct the left subtree and insertions that will construct the right subtree. And rerunning these insertions should reconstruct the tree I start off with. How do I convince myself of that? I write a property, obviously. Here it is. So once again, this is slightly intricate code, but what it says is any tree can be reconstructed by making this list of insertions and just using insert to rebuild the tree. And here I have to use the structural equality. So that's why I need both these comparison operations. OK. So this property says that every tree can be built only using insert. Does it? Is anybody the least bit suspicious about this property as a test? Well, how did I generate random trees? Oh, I only used insert. Wait a minute. This property is saying that every tree that I generated only using insert can be reconstructed only using insert. 0 equals 0. What about trees that are returned by delete or union? OK, so there is a problem, but it's easily fixed. I just have to write a couple of additional properties. One that says that, yes, this property really holds of trees returned by delete, and another that says, yes, it really holds of trees returned by union. And with these two additional properties, then I really am going to be able to test that every tree can be built just using insert. There's one more kind of property I want to show you. They're extremely useful. And they're what I call model-based properties. So once again, suppose we have a tree, we want to test inserting into it, and we want to verify that somehow the result is correct. How can we do that? Well, one thing we can do is take the trees, these complex data structures, and convert them into something simpler. Let me just extract the list of key-value pairs in each tree. Now then, it's hard to say whether the tree on the bottom left is right, but what can I say about the two lists that I've got on the right-hand side of the slide now? Clearly, I should be able to get the bottom one just by using list insertion to insert the key and value pair into the list, right? So this is a very general idea. What we do is we define a mapping from our complex, probably efficient implementation into some much simpler data type. We call that mapping an abstraction function. We abstract the implementation to a model. And then we implement our operation on the model. List insertion is the model of tree insertion. And then I just write a property that says, for this commuting diagram, you get the same result both ways round. There it is. These model-based properties are really simple to write. All you do is you call your implementation, insert, you convert it into the model, using toList in this case, and then you compare that to taking the same input, mapping it directly into the model, and using the model of the operation, the abstract version of the operation. So we're using the simple list functions as a kind of reference implementation to test the complex tree functions. So this is a great property. There's only one thing wrong with it. It's false. Why is it false? Well, quick check shows me, right? It's false because, in this case, I'm inserting the key 1 into a tree that already contains it. And QuickCheck complains that these two lists are different. The rightmost one is the one produced by the model, by list insertion. And what do you know? List insertion does not object to duplicate elements in the list, whereas the tree insertion will never insert a duplicate key. All that means is that list insertion was not the right model for tree insertion. But it's easy to create the right model. All I have to do is delete the key before I reinsert it, and then I won't get duplicates on the list side either. And now this property will indeed pass. And it's a great test of the insert function. So one interesting thing about this idea is that it comes from a paper by Tony Hoare in 1972. He wrote a paper in Acta Informatica called Proof of Correctness of Data Representations. And all you have to do is take the word proof and replace it by property-based test, and you get the same thing. I really like being able to go back to old theoretical papers and turn them into effective tests. I love that. So now I've shown you 5 different ways of thinking about your properties. How effective are they? Well, I'm going to compare 4 of them. The inductive properties are really interesting, but I'm going to focus on the other 4. And first of all, this table shows how many properties I was able to come up with by applying those ideas systematically to the API I wanted to test. So there are 4 ways of building trees, and so there are 4 invariant properties. There are 5 operations under test? No, 4 operations, but I had to write 2 postconditions for find. So I have 5 postcondition properties. Look at the metamorphic properties. I could think of 16 different ways of using that idea to come up with a property that is useful for testing. Model-based tests, only 5. Why is that? Because with model-based properties, you only need 1 property per operation. Each model-based property is a complete test of the function you're testing. OK, so you can see what I told you about the quadratic number of ideas. It really plays out in practice. You can also see that model-based testing means I have to write less code. How effective are the properties at finding bugs? To find out, I planted 8 artificial bugs into my code, 3 into insert, 2 into delete, 3 into union. And these vary from totally blatant bugs to quite subtle. So now we can ask, which bugs can these properties detect? And it turns out here that the invariant properties miss 5 of the 8 bugs. Well, that's not so surprising. They only catch bugs that break the invariant. Of course, there are lots of ways to do the wrong thing without breaking the invariant. Nevertheless, invariant properties are useful because if you have broken the invariant, you want to know that. You don't want to discover it because a more complex property fails. Otherwise, the other kinds of properties together could find all of the bugs that I planted. So that's good. But I want to look in a little more detail at how good each property was at finding bugs. And to do that, I'm going to measure what I call the effectiveness of a property. Let me just explain what I mean by that. If we look at this property, this is one of the postconditions I wrote for find. It clearly calls find and insert. So potentially, if there's a bug in find or in insert, this property might find it. But it clearly won't find any bugs in delete or union because it doesn't even call them. So if we think of the 8 bugs I inserted, 5 of them obviously cannot be found by this property. Of the other 3, how many can this property find? And the answer is 2. So I'm going to say that this property has an effectiveness of 2 out of 3. It finds 2 of the 3 bugs that you might think it could find by just looking at which functions it calls. And then I added up the effectiveness over all my properties and averaged it out by property type. And here are the results. So the invariant properties, they were 38% effective. Well, I already explained that they miss a lot of bugs, but they're still useful, because when they fail, they tell you a lot. Of the others, the postconditions were only about 80% effective. The metamorphic properties were rather better than that. They were 90% effective, but the model-based properties were 100% effective. I said earlier, the model-based properties are complete tests, and that's what we see here. The model-based property for insert, for example, can find every possible bug. Okay, so we can see that the metamorphic properties, well, we can see that a ranking order, and that suggests the order in which we might try to think of properties. Of course, all this says is which bugs can be found by a property. You might also care about how fast can a property find bugs. And I measured that too. So here's a slide that shows the results when I planted a particular bug in union, one of those 3 bugs. And up the top, we can see that the union postcondition finds it. The yellow part in the middle, those are metamorphic properties. They all find it too. And the green property at the bottom, that's the model-based property, which also finds the bug. But what I've also shown here is the mean time to failure of each property. So that postcondition at the top, on average, that needs 50 tests to find this bug I planted. The model-based one at the bottom requires 8.3 tests. So it finds it much, much quicker. Even though, if you think about them as logical statements, those 2 properties are logically equivalent. But one of them finds bugs much faster than the other. How come? It's actually obvious when you look at the code of the properties. You only have to read the first line of each property to understand why. This planted bug is in union. To find the bug, you have to construct 2 trees, T and T prime, that will provoke the bug. And then you have to observe that the bug really happened. The bottom property is only quantified over T and T prime. There's only 2 arguments. It's a model-based property. It checks that every key has the correct value. The postcondition at the top takes a randomly generated key as an argument. To find the bug with that postcondition, you not only have to choose 2 trees that will provoke the bug, you have to be lucky and choose a key that will reveal that the bug really happened. Now, you might be thinking that the lower property contains more code. It's probably slower to test. Well, yes, it is, but it's not. 8 times slower to test, which is what you would need to get the same performance. In practice, the model-based property is going to be much faster for finding this kind of bug. Okay, so that's one example. I looked at all the properties that I found, and I measured their mean times to failures, and then I took the average mean time to failure of all the properties that could find each of 7 bugs. Why 7, not 8? Because I didn't include the bug that screwed up in the invariant and insert, since, as I told you, if you have that bug, the other results are not interesting. But look at this now, and look at the last column in this table. We can see that, on average, the postconditions needed 68 tests to find a bug. The metamorphic properties needed about 60, and the model-based ones needed only around 6 tests. They're an order of magnitude more efficient at finding bugs. So, what conclusion are we going to draw? Well, it sounds from all of this, surely, as though model-based tests are really winning here. Right? They're easier to think of than postconditions because we've got a systematic way of going about it. You think of your abstraction function, and you think of the abstract implementation. You have to write fewer properties than the metamorphic approach. You write less property code. That's good. You only need 1 property per operation. They're the most effective at finding bugs, and they find the bugs fastest. And this has to do with the fact that model-based properties form a complete specification of the code. So, yay for model-based properties. Why did I talk about any others? Because model-based properties can have a big drawback. The model can look too like the implementation. And when this happens, then you're putting your foot in the trap again. And in that case, metamorphic properties are the best alternative. The great thing about them is that they do not require a model. They're the easiest properties to write. You just think, if I change the input to this function, how will the output change? And they are the second most effective kind of property in this experiment. So my recommendation is, first of all, think about model-based properties. If you find that you feel you're writing too much code, your model is too like the implementation, switch to metamorphic. Oh, but don't forget the invariant ones. Again, because if you've broken the invariant, you just want to know that. So there's a little bit more on this topic. If you'd like to know more, I've written a paper about it. And the paper is coming out in Trends in Functional Programming, not this year's, but last year's. Actually, this is a mock-up of the proceedings, because it hasn't actually been published yet. But sometime before too long, it should come out. And if you don't want to wait for that, I tweeted a link a little while back to a draft version of the paper. So if you want to know more, you can just search for me on Twitter, and you will find this tweet. I tweeted it a while ago, but I hardly ever tweet. So you'll find it easily. And just in case you can't read it, there is my Twitter handle. OK. And that's what I got for you.